Okay, lesson 57. Notice it is properties of the definite integral. And a lot of this is just understanding what you can and can't do with integrals. Okay, the properties just tell us what we are allowed to do when we are working with integrals. And so that's what we're looking at. And I mean, I guess somewhat memorizing, but it's not that you just are flat out memorizing these rules. It's just that you're, being familiar with them. Okay. So as we look through these, the first one says the integral from a to b of f of x plus g of x dx. All that's saying is if you have pieces being added, that you can break them up into separate integrals. And we've used that one before because it's just basically saying that you're finding the integral of each individual piece or term. Okay. The second one, we've used this one before. The integral from a to b of k times f of x dx is equal to, and notice what did they do? They pulled the constant out front. And so that's just saying if you have a number, like we had that 4 yesterday, we were able to just pull that 4 out front and worry about taking the integral of the rest. Now, this one is an incredibly useful one, and we'll use it in a couple of our examples today. The integral from a to b of f of x dx is equivalent to the opposite of the integral from b to a of f of x dx. So if you have a reason where you need to flip-flop your limits, your boundaries, so you want them to flip-flop, you can flip-flop them and then it just makes it a negative out front. Okay, so we'll use that one down below in our examples. This next one is a good one to know. The integral from a to b plus the integral from b to c if you have an overlapping boundary. So the top boundary over here matches up with the bottom boundary over here. That is equivalent to adding them, and it's the integral from a to c. And this is, of course, if the insides, it's all f of x. So from a to b, b to c, you can add that, and that becomes just one integral a to c. And we'll use that one in our examples also. Okay, so again, as long as that b matches, you can combine them.
But the a and the c don't have to match? It's just the two?
Right, yeah. Because the a and the c then carry over to your final answer. And some of these will make a little bit more sense once we actually use them in an example. The next one's a really good one to know too. The integral from a to a. So if your boundaries are the same, your integral will always equal 0 every time. Okay, so in other words, you don't have to even work out that integral. If the boundaries are the same, you know it's going to equal 0. Let's see, I've lost my spot. Where am I? There we go. Next one. If a function is greater than or equal to 0 on a certain interval. So if a function is positive on a certain interval, then the integral on that certain interval is also positive. And also remember, area or integral is area under a curve. So this is saying if a function is positive in a certain area, then the area is also positive. Okay? If a function equals 0 on a certain interval, then that integral also equals 0. So the area also equals 0. If a function is less than or equal to 0, so negative on a certain interval, then so is the integral. It is also less than or equal to 0. Okay? Carrying along with that same idea, if g of x is less than f of x, so if one function is less than the other function, then same thing is true of their integrals. And finally, if two functions are equal on a certain interval, then their integrals are equal. So some of that seems to me kind of logical. And some of it, I think, if it doesn't seem as logical, will make more sense just as we use integrals more. So let's look at example 1 here and see if you can make any sense of it. So it's all about using the properties we use today. Okay? Let the integral from -1 to 1 f of x dx equal 7. And the integral from 1 to 4 f of x dx equal 2. Evaluate, so we need to find the integral from -1 to 4 of f of x dx. I agree. It says,
Oh, wait, what did you say?
Just gonna add up the 702.
okay. Essentially, okay, so look at what happens. The integral we're trying to find is the integral from -1 to 4 of f of x dx, right? That's what we're trying to find. Well, notice, what are the pieces they give me? They give me one that goes from -1 to 1, and they give me another that goes from 1 to 4. Notice what's overlapping.
Ones and the ones are the same.
The ones are the overlapping. So the top boundary of one and the lower boundary of the next are overlapping. So this is the fourth property down from the top of the page, the one that was the AB and BC, and it equals AC. So what this is saying is that this is equal to the integral from -1 to 1 of f of x dx. My pen is giving out on me. Plus the integral from 1 to 4 of f of x dx. Okay, so -1 to 4 is equal to -1 to 1 plus 1 to 4. And what do we know? The -1 to 1 is 7. The 1 to 4 integral equals 2. And 7 plus 2 is 9. So are we okay with how that integral, that idea works? And it's one of those they'll randomly come up as we go through problems, okay? So, I mean, we're learning it or using it today, but it's just one that you need to be familiar with. Let f and g be functions such that the integral from 1 to 3 is 4, and the integral of f of x, that is, and the integral from 1 to 3 of g of x is -1. Now, honestly, you may be able to just kind of see it as is. You may not need a lot of work. I'm going to kind of break it up because I want you to see all the pieces here. So first of all, I have the subtraction within a single integral. The subtraction within a single integral could be broken up into two integrals being subtracted. So the first thing I'm going to do is break this up. The integral from 1 to 3 of 3 f of x dx minus the integral from 1 to 3 of 1/3 g of x dx. So that's one of our properties we can use. That was the property towards the top, right? Technically the very first property. What else can I do?
Simply just plug it in.
Yes, but officially, we don't have an integral from 1 to 3 of 3 f of x dx. We have the integral from 1 to 3 of f of x dx.
Okay, so you can't just multiply by 3.
Well, I mean, we will, but official notation, where should that 3 be? What can we do with it constant? It can go out front. Okay? And I get it. That's why I said you can pretty much do this in your head without putting down a lot of work, but just trying to make sure you guys understand the properties. So the idea that this can be written as 3 times the integral 1 to 3 f of x dx minus 1/3 times the integral from 1 to 3 g of x dx. And so now, do you see all the pieces? It's 3, and then integral from 1 to 3 of f of x dx. What is that? Integral from 1 to 3 of f of x dx up in the bar, or in the directions defined as 4. Minus, then this next part we have a 1/3 times, what's the integral from 1 to 3 of g of x dx equal to? -1 according to the directions? So 3 times 4 is 12, minus a third times negative 1. So a third times 1 is a third, minus times minus makes it plus a third. 12 plus a third. You could go as easily as saying 12 and a third. A AP Calc multiple choice would not necessarily have 12 and a third. 37 thirds. Because 3 times 12 plus 1. Okay. Let's try another one. It's all in terms of f. We've got an integral from negative 2 to 1, an integral from 3 to 1. They want us to find the integral from negative 2 to 3.
What do we use for the second, whatever it is? What do we use? The one where we can flip it to make it times the negative sign.
Okay, so as we look at this, in the end, we need the integral from negative 2 to 3. Here we have a negative 2 on the bottom, which is what I need. I need my other integral to have a 3 on top. It has a 3 on bottom. So I can't just add these as is, because this is the one that was a to b plus b to c, and the b's were the same, right? The diagonals were the same. Here, I have a b, and then this one, the 1 needs to be right here. And so the idea, so these 1s are in opposite locations, is take this one, and if you're going to flip the boundaries, 1 to 3, what did we have to do? You had to multiply by a negative. And so we can write it as the negative of the integral 1 to 3 f of x dx. So now, think about this. I have the integral from negative 2 to 1 of f of x dx plus the negative integral from 1 to 3 of f of x dx. Do my ABCs make sense now? I have negative 2 down here, which is kind of like my A. B is 1. Then over here, B is still 1, so those diagonals match. C is on top is 3. So when I add these together, since the 1s are the same, negative 2 and 3 are my new boundaries, and is that what I was looking for? That's what I was looking for. So, put the numbers in. What did we have? The integral from negative 2 to 1 was equal to 3. Plus negative of the integral from 1 to 3 f of x dx. It's going to be equal to 7. 3 plus negative 7. Really challenging math of negative 4. So again, properties to be familiar that you can do that stuff, because there are times where that will definitely make life easier. Okay, you ready for the word problem of the day? Assume f is a positive valued continuous function over the interval from 5 to 8. Assume also that the absolute maximum of f over the interval is 12, while its absolute minimum over the interval is 3. Using the properties of this lesson, state the maximum and minimum values possible for the integral from 5 to 8 of f of x dx.
Lots of information.
It is. It very much is.
Okay. Let's tear into it.
Pair into it.
Break it down.
I like to use a picture on this one to help it make sense. Have some hope here. So I'm going to make a big graph. Just a first quadrant graph. And here's the deal. I have to be able to include the interval from 5 to 8. And we have to be able to go as high as 12 to see what's going, So along my x-axis, 1, 2, 3, 4, 5, 6, 7, 8. So there's my 5 and 8. Now along the left, I'm going at least up to 12. I'm labeling my 12 specifically, and then my minimum of 3. So I'm labeling those. You guys can't see that I labeled my 5 and 8. There you go. Are we there? Okay, so first of all, we're on the interval from 5 to 8. So I'm going to kind of draw dotted lines. Does the rest of this graph matter? I mean, in terms of left and right of 5 and 8, we're specifically zeroing in from 5 to 8 because that's what it says on the interval from 5 to 8. Now, it says we're assuming f is positive valued continuous. So positive valued, we're talking above the x-axis. Continuous meaning some kind of curve, right? Some kind of curve continuing on. Assume also that the absolute maximum of f over the interval is 12. So what we're saying is, in this interval from 5 to 8, my graph, the highest it will possibly go, is 12 right there. The absolute minimum, so the lowest it will ever go, is 3. And I have some curve in there. So I'm going to just, and we don't know what the curve looks like, okay? But if I sketch in a curve here, whoops. Oh, okay, I went over too far. Well, past those dotted lines, it doesn't matter, but I was trying to do a kind of just a, I don't know, an S curve, but okay, so there's just a random, I drew that curve in there. Okay, we don't know what it looks like, but just drawing something in there. Okay, integral. What does an integral mean? An integral is defined as what? Area under the curve, right? Okay. So, area under the curve. We are specifically on the interval from 5 to 8. The maximum height I could go up to is 12. So if we're talking about the maximum here, thoughts on what that max area is? Well, don't think that difficult because we know the max value is 12, right? And we're on the interval from 5 to 8. We don't necessarily know what this curve is. You know, maybe it goes more along here, maybe it's at 12 more. But this height is what? This height is 12. And what shape have I drawn here? A rectangle. So if the rectangle has a height of 12 and a width of 3, What could that max value be?
Would the height on
Wouldn't
that
it be
be
less
12?
than 12 since you didn't start at 0? Since you started at 3?
Yeah, it would be.
Say what now?
Since you started at 3, it wouldn't be a height of 12.
Then wouldn't that be a range of 4?
0 to 12 would be a height of 12 when you start.
Okay, we didn't start at 3. Okay, we didn't start at 3. This is just the minimum, like the lowest the graph would go. The graph wouldn't go all the way down here. Okay, but when you're finding area under a curve, it goes from the highest point down.
Oh,
And so, like, for instance, at this point, if this graph went all the way across, which we don't know what the graph looks like, okay? But if this graph went all the way across, it would go as high as 12, and then it would have a width of 3. So that max there is a 12 times 3, because length times width, right? Length times width being 36. That is my max possible value. In other words, is it likely to be exactly 36? No, probably not. Okay. I guess what I should, we're doing area under the curve here, right? So maybe if I, draw that in, it goes all the way down to 0 here. Now, what if instead here we're at the minimum possible value?
that's 3 times 3.
Then at the minimum possible value, we have a height of 3, and we still have a width of 3. And 3 times 3 is 9. And so that is my minimum possible value. So it's unlikely that it's all the way 36. It's unlikely that it's all the way down at 9. It's somewhere in between. But we're trying to find the minimum possible value and maximum possible value. So we know that that integral there is somewhere between 9 and 36. Okay? And so how I was going to write my final statement is that 9 is less than or equal to the integral from 5 to 8 of f of x dx, which is less than or equal to 36. That's kind of my summary statement there, showing that the integral is somewhere between 9 and 36. It's less than or equal to 36, but greater than or equal to 9.